Good morning.
Good morning and dzień dobry. Good morning on this Saturday morning. I'm very excited to actually be able to talk to you about my work that is focused on safety and robustness for deep learning with provable guarantees. First of all, I wanted to say thank you to the organizers. And I hope that I will be able to meet many of you in person and not just virtually. So to begin with, I wanted to set the scene. I think you are probably aware, even by reading the news, that deep learning has made tremendous strides recently from research into real deployment. The actual idea of neural networks is not new. In fact, it was proposed in the 1940s. And since then, it sort of has been developed slowly. But around 2000, the field has exploded. And now we have many types of deep learning neural networks. And what we also have is successful deployment in many applications. And in particular, I think the media has focused on the vision breakthrough win at Go, but the community, the research community of computer scientists has actually recognized progress with deep learning with the Nobel Prize of Computer Science, which is the Turing Award. So you might, looking at the dates, be asking, but why now? It's an old idea from the 1940s. Well, of course, this is because of big data. I have a lot of Instagram pictures that have been labeled, so this can be used for training. We also have PyTorch and TensorFlow, where it is easy to actually devise the models. Inference has made progress, and of course, now you have GPUs not just in your computer, but they are already developing automotive-grade GPUs, to actually run autonomous cars. So because of that, we now have deep learning with everything. I've already mentioned autonomous driving, that's one example, but there is also face recognition, medical diagnosis, and the stakes are rising even higher. If you are following what Elon Musk is doing, he's now focusing on brain-computer interfaces. And I think this is something that will grow into a bigger field. Now, against this background, the question that I'm asking, and I have been working with engineers in the Oxford Robotics Institute, who are developing software for autonomous cars and computer vision techniques as well. I mean, my question is, well, if we are deploying these techniques, should we worry about safety? And what I'm showing you here is an example. A few years ago, there was a challenge called the Nexa Challenge. It was a challenge issued by the community to develop a neural network that will take dashboard images from cars, and these are actual dashboard images. The idea was to develop a network that would classify these images into those that have a traffic light and whether this traffic light is red or green. Okay, so these are, real images. Now, what my student Matthew Wicker has managed to do is to develop software, and I'll say you a little bit more about it, that it will find a position of just one pixel, change one pixel in those to green, and then an image that was classified as red actually changes to green. So imagine you are sitting in your Tesla, and we know that Tesla uses ordinary cameras. And in that test life, there is some adversary that manages to change that pixel, that Tesla will suddenly start moving forward. Of course, I'm dramatizing here because I think I imagine that Tesla would actually try to make sure that there are other checks and balances at that point. But the focus of my research has been for a few years now, how can we ensure that such behavior cannot occur? Of course, I told you about an attack that was on the image, just changing a pixel. But in fact, what we also need to worry about is physical attacks. And this is an example of resilience testing, which was done by McAfee. Resilience testing of a Tesla 2016. It was done in a car park, so it was all safe. What they've changed is the digit 3 in here. As you can see, it's slightly elongated, and it confused the computer vision software. It actually misread it as 85 miles per hour, and the car suddenly started accelerating. Well, I mean, these are, okay, sort of artificial and real physical attacks, but in fact what we have also seen is that there have actually been fatal accidents, both of the Tesla, which relies on an ordinary camera, and also Uber, which uses LiDAR for image recognition. Now, the question that engineers who are actually deploying these software components based on deep learning, they might be asking, but, you know, how is that possible? I was told that this deep learning network has 99.9% accuracy. And I will explain how this is possible. So deep neural networks, it's already known in the community that they can be fooled. And in fact, this has been known in the community since around 2013. And there is now a very widely cited paper which introduced the concept of these adversarial perturbations. Adversarial meaning there is an attack. And the idea was, if you take an image, in this case, a panda, and add noise to that image, but, you know, just a very small proportion of that noise, then it would suddenly classify it as something completely different, say gibbon or oven. Now, this is artificial white noise in this case, but I think the examples that I've showed you, also the physical attack, this is a potential risk, safety risk, and the potential security risk as well. If you can get access to an image and change it and actually cause the network to behave in an unstable way. And I'm showing here an example of an image, but adversarial attacks have been demonstrated also for many other types of applications. And in fact, they just transfer between network architectures. So where I come from is the field of software verification. And this is something that I have been working on for more than 20 years. The idea is that if you have a program or a computer system, and there is a program there on the left, what we do is we develop models, rigorous mathematical abstractions of these programs, either before they are deployed or perhaps as a legacy. And the idea of developing these models is that you can then exercise them, you can stress test them, which we call verification, against specifications. Now, this verification will actually develop a mathematical proof, but this proof can be computed using an algorithm. So we run proofs in computer software. So verification against specifications is one, but another aspect that's also being developed is given a specification, can you then optimize the model so that it is correct by construction, actually guarantees that the specification is satisfied. And as I said, these techniques are automated. We run models and proofs in software. So when I started working on this 5 years ago and looking at the applications in the Oxford Robotics Institute, I became interested in deep learning. So what this talk is going to do is just to give a brief high-level overview of where I am now, having started with a keynote at CAV, which is the main computer-aided verification conference in 2017, and how I have now focused on different applications and trying to develop algorithmic techniques that would produce provable guarantees for robustness, which started with adversarial robustness, but now it's moving beyond adversarial robustness towards probabilistic safety, and also, I'll say, a little bit more causal interventions. Okay, just to set the scene for the approach. What we are dealing with is deep learning, a deep neural network. A deep neural network is arranged in layers. Each layer has a number of neurons and they are connected. In fact, each layer is a linear transformation. What the neural network inputs is an image, and an image is a point in a vector space. It is, in fact, a 3D array of pixels, and that image is transferred through the layers, the linear transformation plus activation function, until towards the end, it will produce a score, typically by something like softmax, and it will choose the most likely label for the image. And in this case, car. So it got it right. Okay, so formally, the problem setting is as follows. Because I have a number of layers in a neural network, I have several vector spaces, with the input space being the vector space of 3D images. And then, okay, because I'm focusing on image classification here, a good question is, what should a specification be? Well, the specification for an image classification, in fact, it's very difficult to define precisely. So in fact, what we are going to assume is them being given a function as a specification, and that function just simply models human perception ability. And this is going to be the standard that we compare our solution to. And the neural network would then approximate this function f from a number of training examples, and these are just simply pairs of images and labels. Now, as I've already mentioned before, the network is arranged into layers, and it will also, the training process, we use optimization to learn the weights and the bias of each layer. Okay, and the neural network, the small f, given an image, will then produce the class that's assigned to the network. So, training and testing. So once you've chosen your architecture for a neural network, what you then need to do is to train it. And the example here tells you what is happening. So what we have is a problem which has two classes. There are the light blue crosses and the red dots. And these two classes, obviously, in this case, since we are talking about images, they would have infinitely many points. But what we train is we train from finitely many points. Now, what this picture is also showing, that the task decision boundaries in a dotted line, it's not known precisely, but the model decision boundary in general will not align. And this is all well known. So in order to check whether the trained model is doing what it's supposed to do, what is done in the community is model testing. So we had a training set, now we have a separate test data set, which should follow the same input distribution. And these are the darker blue crosses. And your accuracy is simply the number of times that the network got the answer right on those blue crosses. But there are only finitely many, but infinitely many points. So what the Segedi, 2013 and BGO papers have noticed that if you actually start from a test point and use optimization to try to move towards weaknesses in the model, and these weaknesses are either the decision boundaries, as in some examples here, or points, say, going in between the points, because perhaps you have not included a test point to identify some case. And this is how adversarial examples are created. They are artificial points that are actually found algorithmically by searching for them. And then what's the point of finding adversarial examples? To expose weaknesses in the model. Now, what I'm focusing on is actually the dual problem. So adversarial examples, adversarial search aims to find witnesses of the weakness of the model. But on my side, I'm working with the dual problem. I try to rule out that such adversarial examples exist. So, I want to make sure that the classification, if you consider, say, the problem of image classification, and I have an image X, there will be a region of points around that image, and I want to make sure that the classification is invariant on the whole image. And this is known as pointwise robustness or local robustness. I'm going to adopt it as the very, very basic notion of safety. And really what I'm trying to say is that the decision supported by this region is safe if it is invariant. Okay, so there does not exist a point Y whose classification is different from the classification of the point X. Now, of course, I'm assuming here a trained network. I'm also assuming that someone has given me the diameter for the support region. It can't be too wide, because then some of these misclassifications may actually be true misclassifications, not adversarial. I also assume that I know what norm I'm working with, and in computer vision, we want similarity, but in fact, we work with weaker norms that are simply just proxies for image similarity. And you can also strengthen this definition by focusing on a group, a class of manipulations that you then want to ensure that your decision is invariant for. Okay, so my aim is to then strengthen the analysis of the network's robustness beyond accuracy. I was showing you the accuracy is computed by those dark blue crosses, and you can search for adversarial examples. But if you've found an adversarial example, okay, you can then try to fix a network. But if you haven't found it, it doesn't give you enough information to deduce that the network is safe. Now, in my case, I want to have these green regions where I rule out that there is no adversarial example. So model verification is strictly stronger in that sense. And the very first approach that we tried worked with these regions. And because we are working in vector spaces, the region of the point is actually infinite, so there are infinitely many points. The idea of ruling out adversarial examples and using that as the provable guarantee is very simple. It is based on discretization of that region, and that discretization can be obtained under some assumptions, and for example, using Lipschitz conditions, so that I can reduce, the search of an infinite region to just checking the grid points. In that particular example, what we did is we used satisfiability modular theory and tried to scale the method by propagating verification layer by layer. The main strength of that approach was that it allowed me to deduce, if I haven't found an adversarial example, that one does not exist, which is not the case with heuristic search. Even the strongest heuristic searches for adversarial examples because they are stochastic. But I need to know, for example, some upper bound on the Lipschitz constant. Okay, so how do we improve? How can we improve on this? How can we actually search for adversarial examples in these infinite, high dimensional and nonlinear spaces and in, infinite regions? So my students' idea was to then apply structure to the problem. So, I'm showing you here an example of a sort of very large image, but just think back about these Nexa dashboard camera images and try to find the position of the single pixel. It's exactly the same problem. Now, what we did in this work is we actually employed the SIFT algorithm. This is a well-known method in computer vision, which will take an image. So this is outside the neural network. The image is input into a neural network, and then it will learn the features in the latent space. But separately from that, what I can do is I can use SIFT to extract features, and I can build an intermediate representation of the image as a mixture of Gaussians. And what you see in the middle there is which features it's found. It gives you the importance of the feature and the position of the feature, and also the mixture of Gaussian representations. Now, this is an intermediate representation, which I can now use in order to improve my search. In fact, what I do is I will then target the search to the most important features in the image. Then I do it by setting up a game. And in fact, there are two variants. There is a cooperative and a competitive game. I will just give you the sort of high level view. I have two players in that game, and the game will have access, can query the network, but it will also work with this intermediate representation as a mixture of Gaussians. And the idea is that player one will select the feature to manipulate, so it will target the most important ones. And once player one has made the choice, player two will select a pixel within that. Now, the goal is finding an adversarial example. Okay, this is a search. Any adversarial example that you find will actually approximate what we call the maximum save radius. So this is the radius around the point such that within it there are no adversarial examples. An upper bound will simply produce an over-approximation of that maximum safe radius. So it is a guarantee that there exists an adversarial example above it. And as a reward, I'm going to choose the inverse of the distance because I want to look for the worst possible. The worst possible are the ones that are the closest to the actual image. So what you can do with the game is you can use to approximate an upper bound, you simply search, and in this case we use Monte Carlo tree search. This is a finite game tree, but you can also compute a lower bound on the maximum safe radius, a lower bound on the MSR, and the lower bound on the MSR will actually rule out adversarial examples in the region bounded by the lower bound. So I have an interval around MSR that I can compute, and getting the interval smaller and smaller will improve the kind of guarantee that I have. So just to show you how this works, I start with this image, the NIST image 7, and I'm showing the blue states are states of player 1, and then player 2, once a feature has been chosen, lambdas are features, player 2, and then select a pixel. And the images below show you the modifications of the images, or the one with the blue border still classify as 7, and at some point 7, the one in the red border, is classified as something else. And what does it actually allow you to do? So this is an image which is taken from the GTRSB traffic sign benchmark. So it is a traffic sign, and at the top you see images that are adversarial. So the classification is incorrect, and the images below are not adversarial, they are safe. They are very slight modifications of the original image. You can also see the convergence trend of the upper bound, but I should point out that the interval between the upper and lower bound is still very high because we have different scales on either side of this. Okay, so far this is for images working with convolutional neural nets, but what you can also do is you can generalize the method to videos, where in this case what we are working with is a CNN extracting the features and an RNN, recurrent network, processing the frames. And the manipulations, the adversarial manipulations, will actually operate on optical flow, which is the difference between the frames. I'm showing you again examples of safe and unsafe perturbations and how you can show that the bands converge. So this could be used, for example, to show that your video is resistant, the classification of your video is resistant to some natural distortion, such as lighting conditions, etc. And beyond that, what you can also do is you can show, you can adapt the game-based, in fact, the maximum safe radius approach and the game-based method as well to text classification. This is because text is also represented via word embeddings in terms of vector space. And what I'm showing you here is some examples of adversarial attacks, so replacements of words in a text classification system, say news classification, that would potentially catastrophically change the classification. Some of them are grammatically inconsistent, but others are actually believable. So they can be viewed as adversarial attacks, but they can also be viewed as just lack of semantic robustness in the model. And what we can do is we can then, for, say, a given text classifier, we can produce certifiable guarantees. And this can be done at a word level. So we can identify words that, however you perturb them, the classification will not change, but there is also in the words in red shows that the classification is very vulnerable to changes in those words. Okay, so far the maximum safe radius, that's what I have focused on, but what has it allowed me to do for the Nexa? So these are the dashboard camera images. Now, what we did is we were able to take the test data set for the winning Nexa network, and for each of the images in the test data set, Matthew's software was able to find in less than a second, and on average, 3 pixel changes, just 3 pixel changes, and the classification was different. So in fact, we took a network which on the original test data set was 95% accurate, but by slight modifications to each image, on average 3 pixels, the network's accuracy went down to 0%. Okay, those of you who are from machine learning will probably know that I'm playing around with input distribution, but if you are, an engineer interested in deploying these solutions, you want to have stronger guarantees. Because these pixel changes can actually be simply noise. It doesn't have to be adversarial. This is within the limit of noise. Okay, so that's what we did with MSR, but how good are MSR guarantees? So just to recall, for MSR, the maximum safe radius, I focus on a point, so essentially work with local robustness, and I try to approximate the maximum safe radius, because this is not tractable in many cases. I compute some lower bound approximation and some upper bound approximation. And there are many advantages of working with, say, something like the game-based method, because it is model agnostic. I don't have to adapt the technique as to whether it is a CNN or an RNN. In the way that, say, CNN, CERT, or popcorn, could be. The relaxation methods actually have to be adapted. It can be configured with different norms and metrics, and it can also be adapted to discrete search spaces, such as words. That's what we have. So even though for words we use word embeddings to represent them in a continuous space, words are essentially discrete. So what you need to be able to do is to also work in a discrete search space. But I need to say that this notion of robustness expressed in terms of MSR is very, very simple and very, very limiting. So in fact, what we need to do is we need to build on this. And in particular, I'm highlighting here 2 possible directions that I've taken with my group. One is to consider robustness to more complex properties, in this case, interventions, and the other one is actually provable deterministic guarantees are not workable. What we also need is to consider probabilistic guarantees, because there is a lot of uncertainty that we have, and we have to account for the learning process. Okay, so robustness to interventions. Okay, so in this case, what I'm going to focus on is to what extent, if I develop a model and say, think of a traffic sign recognition system that you develop in California. So you've developed it in California using images, from California, and then you want to sell your module to the UK, okay, and you want the same software to work, for example, in November skies in London or in Oxford. So this is known as distributional shift. I'm actually changing the distribution of the input images because each environment will produce a different distribution. Now, in this particular example, I don't work with neural networks. I instead work with Bayesian networks and causal Bayesian networks. What Bayesian networks are graphs over random variables. So random variables are data generating processes. Say if you focus on an insurance company, the insurance company will have data and it will be able to identify from those random variables that age influences risk aversion. Older people are more risk averse, for example, and age also influences the medical cost because younger people tend to have more accidents. Now, a causal Bayesian network will identify edges between these random variables, and the idea is that a shift in age will influence a shift in the medical cost. So this kind of causal Bayesian network would be, what an insurance company would have. They would have the data. They could, identify the causal or, strong correlation links between this Bayesian network. But then they would also have the insurance policy. So imagine you now have a machine learning component F, which you're training whichever way you want. And that decision function will obviously need to access this data generating process. And what I want to do now is to actually stress test that decision function under shifts in the distribution. So in particular, under what I call causal interventions. And there are two types of, for this I define an interventional robustness problem. And notice, so what you see, there are two images. Notice that I have now added the function f. It's a discrete function. So that function takes as input values from that data set, and that function I want to compute robustness guarantees for. And I do that by computing the worst case probability. Okay, worst case probability. In fact, I can compute an upper bound again and the lower bound as before on the worst case probability. And I can do it in two ways. One is a simple, that is, in what way f is affected by the change in the values of the parameters, that is the change of the conditional probabilities. And the other one is in what way the robustness is affected by a change in the graph. So you can actually add or remove links, edges. So you can introduce dependencies into the network. And this, because this kind of inference in Bayesian networks is not tractable, What we do in this case is we work with a compact tractable representation known as arithmetic circuits, a kind of probabilistic circuits, and we can compute upper bounds and also lower bounds on this interventional robustness probability, and we can do it fast for the type of applications. Okay, so that's causal interventions, but one other thing that I want to highlight is that the deterministic guarantees, and in fact requiring that no adversarial examples exist, are just too strict. What we need probabilistic guarantees, and we need to take account of the learning process. Now, if you consider neural networks, there is a variant of neural networks known as Bayesian neural networks, which simply introduce prior on weights, and then you compute the posterior probability in the conventional Bayesian way from the likelihood function. This is also intractable, but there are various approximate variational inference methods that can be used for training in this case. But what I want to do is now I want to consider the safety property that I had before. But before I was saying, well, my safety means that the decision has to be invariant in that region. That means that does not exist that point Y. But now I just change it to defining it so that the probability of such a point existing, a point that has a different classification from X, that probability is very small. So it's bounded from above by some small value epsilon, and that probability is also conditioned on data. So for that, we have developed two approaches. One is based on Monte Carlo sampling, and another one based on numerical approximation using an optimization technique to actually, again, compute bounds, lower bounds, and in some cases, upper bounds on those probabilities. And we have used it in the context of an autonomous driving example. This is an end-to-end controller. So you can think of an end-to-end controller which takes images, dashboard camera images, and produces controls. There was a network developed by NVIDIA. We have developed a Bayesian version of the network. We didn't train it on real images. We trained it on images from the color simulator. But we have used the robustness evaluation framework, the framework that computes the probabilities, to actually check the probability of maneuvers being safe or not, depending on various conditions. So one is approaching an obstacle, and another one is the change in the weather, rain or snow, which you can do using something like the color simulator. Okay, so that's more or less, so summarizing, I mean, there is much excitement about AI deployment, and I've already, given you these examples before, but at the same time, I think if you have watched the news, there is a bit of backtracking, and in fact, there have been some embarrassing withdrawals of certain systems that were introduced because Alexa's privacy or Apple's Face ID defeated, or IBM's Watson was actually overpromised, and for this, I think my approach to focus on robustness and developing tools to actually compute provable guarantees on robustness, especially in safety critical scenarios is what I put forward and I argue for the community. But in fact, we need to make even more progress and to go into connections to cognitive science and psychology, because even if I develop a perfect system that would compute guarantees, deterministic guarantees and probabilistic guarantees, it will not be sufficient to handle the recently publicized examples where people are just getting fed up with autonomous cars because they are too conservative, they can't handle the roundabouts, and their decisions are not human-like. So what we also need to do is we need to develop these systems so that their decisions are more human-like, but of course that introduces new challenges for the robustness, and verification, because now we need to have models that can represent, say, emotions or other mental attitudes. So I will just finish by, summarizing that, say, the main lesson learned is that we need to evaluate deep learning more critically, especially as we introduce it into safety and security critical situations. And I've given you an overview of methods which have been shown to work on small networks across a wide range of applications. And I want to highlight that, there is a lot more work that we need to do, and I can't do it on my own. So I want to encourage people to sort of follow in my footsteps. And I wanted to credit my funders and in particular the Advanced Grant Fund model, which is focused on automated and especially probabilistic reasoning for deep learning. Thank you.
Thank you so much for this very interesting lecture. We actually have a number of questions asked at the chat. So let me ask the few of the top-rated ones. Let's start off with this one. Have generative adversarial networks been proven to be useful in finding adversarial examples? And the Basili also says that, yeah, the question kind of comes from the fact that GANs quite naturally seem to be similar to this two-player game approach that you've been talking about.
Exactly, yes, that is a very good point. Yeah, but generative adversarial networks, I think their aims are different. They want to, on the one hand, they want to train networks that are more robust. In my approach, I have assumed I have a trained network. Mm-hmm. Okay, so you can even take a network that's trained using GANs, mm-hmm. and with my approach, you would then have, an additional check in case something has been missed.
I see.
But the idea of a game is very, very similar.
So this actually relates to another question asked by Artur. So can this approach that you've presented be used to improve the robustness of neural networks via some sort of feedback loop, like using the MSR as a loss or attention mechanism? Or is it, so part of the question is, or is the method specific for post-training analysis? I guess this quite closely relates to this question about GAN.
Yeah, no, I think these are all very good points. So when we talk about deterministic neural networks, we have not used MSR in loss, but other people have done that. And they are trying to combine this kind of verification with retraining. Mm-hmm. And the original approaches also worked from adversarial examples. The idea is to identify some adversarial examples which would actually be helpful to improve the robustness of the network. So no, I have not focused on this. Other people have, in particular Martin Vechev's group. We have done something similar for Bayesian neural networks. So we can actually do certifiable training for Bayesian neural networks by incorporating this kind of aspect in the loss function. So that's a very good point.
Just so that I understand correctly, that is used in a way to mine examples for feather training. Or
No. Okay, no. So I'm confusing. There are two separate things. Originally, when adversarial examples were introduced, people tried to come up with defenses, and one proposed defense was, to add some of these adversarial examples to training. Unfortunately, it was then discovered that these adversarial training with these adversarial examples can bias the network.
When you say bias the network, decrease the performance by proxy.
Decrease the performance, but also, you have better performance on adversarial examples, things where you should not have.
I see.
Yeah. I mean, the history of, say, adversarial examples, of course, GANs are the best method, but to start with, the research progressed through finding yet another method of attack and a defense, but all the defenses have been broken.
I see. So, and then you said that the one category of progress at the very beginning was this finding adversarial examples, trying to retrain on them, and then you I think were to move on to the second large approach. And that is to a large extent what you were presenting today. Okay.
Yeah.
So another question we have is, can these approaches be extended to verify global properties of trained models? For example, the model will never yield a different prediction when a single pixel is perturbed.
Well, okay, so it depends what you mean by global. I think we have done it using a reduction to tensors for certain types of networks. Global meaning computing expected MSR over the data set. Okay, so over the test data set. So you still compute it for finitely many points.
Right.
I think global in the sense of, the full infinite space, I think you really need some additional assumptions, and you need maths in a way that, say, control theory can handle these situations.
Affirmative. Yes, that absolutely makes sense. One other question from Patrick Mijoua on the more mathematical, I guess, aspect or statistical aspect of your methods. How does the idea of safety region deal with the fact that the highly dimensional spaces are very sparse in a way that we can fit a lot of unique balls into a unique cube?
Okay. No, it doesn't. It can't. I have not said, what shape that region is. Maybe, you could work with some other shapes to adapt this. But, working with standard LP balls, it does not really help. You can try to work for other approaches. We have worked with Mahalanobis distance, which is a similarity distance. I think you really need to, come up with a good metric and a way to identify the support region for the decision. I think in my work, I've assumed that someone has given me this, a trained network, and also someone has told me what the critical support region for the decision is. And the intuition is, if you want to recognize, red traffic lights, I think you know what these would be.
I see. All right, and I think this will be the time for one last question, actually the top voted one, I believe, and that is a very, very high level question from Stanisław Jastrzębski. When do you think it is likely that we will have fully autonomous self-driving cars? Since you're clearly involved with with this line of research at a very high level, and the follow-up, and do you think that it can be achieved by scaling up our current methods, or do we need to develop novel AI algorithms to get there?
Okay, so yeah, people ask me this question, I think, every time. I think I would say depends. I would say on a highway in California, autonomous driving in sort of short sections, that's a solved problem. I think if you try to take the same car, the Tesla, and drive it in a slip around Oxford, it is not. And I know people have tried, and that was not a pleasant experience for them. Okay, so that problem is not solved. The problem that is not solved is also the handover, because Tesla is, of course, not an autonomous car. The driver is in charge. But I think for that, in order to develop a proper way to hand over, I think you really need to incorporate more cognitive, I think, information, and to what extent we will be able to accept this, or whether this will be considered intrusive or not. I think there are already various, monitoring techniques. So I think there are different answers, and I would say a very long time. I think as you probably know, that we are already past the date when Elon Musk promised autonomous driving and various other car manufacturers. So there are two answers. One is it will either take a very long time or never. But I think we will still benefit in many, many ways, because the technology, I think, is improving, and it will certainly improve driving, but we need to understand to what extent, how we can use the technology so that it is safe, but it also works well with our, kind of wishes as a human for privacy and, various other things.